The last feature I want to touch upon of NMR spectra is the chemical shift. And the chemical shift is an indication of where the signal is located along the x-axis. For instance, if I show a NMR spectrum, such as this, these are your chemical shifts, 1 ppm, 2 ppm, and so forth. Now, before we take a look at specific effects on the chemical shift, I want to describe what it does mean to have a high ppm and what does it mean to have a low ppm. Here's your x-axis, and the units are going to be parts per million, and we'll start here at 0. You could have negative ppm, but we won't see that, and most likely you won't see that either in any of your examples. There's a standard that's added, a little like a microliter of trimethylsilane, and the spectrometrist or the operator or the grad student will set that to 0, and typically you go all the way up to 10, and we have maybe a signal here and a signal maybe here. Okay, so this is obviously that's 0. We'll call this 1.0, and maybe this one 7.0 ppm. Okay, what does it mean to be a low ppm? As you go to lower ppm, that is typically called the proton is being very shielded. It's good to understand, or at least be able to recite these different terms. So for instance, the signal at 1 is more shielded than the signal at 7. We'll talk about what it means to be shielded in just a bit. Let's see, what else? Let's go the other way actually. And going in this direction, it is called deshielded. We're more often going to be concerned about signals being deshielded, getting pushed to the left from a base amount of ppm. Let me give us actually also a definition of chemical shift. Chemical shift, the symbol is this little delta, is the difference in resonance frequencies caused by differing amounts of shielding. Differing amounts of shielding. The definition itself is not that useful, but the concept of shielding is very useful. Let me find a better pen. Okay. This idea of shielding. If we have a proton and it's feeling the effect of, a magnetic field, external magnetic field, but we also know, and we also saw in a previous video that, this particular proton, we'll call it proton A, is affected by the mini-magnets produced by neighboring protons due to its proton spin. Either going with the magnetic field or against the magnetic field. So with and or against. Okay. Now the thing is, if there's a lot of electrons surrounding that proton or near that proton, you'll have another effect, unfortunately. I know the effects are piling up, but you know from physics that electrical current can induce or can create a magnet. Where have you seen that? You wrap a copper wire around a nail, pass a current through that wire, you'll make that nail magnetic. And vice versa. You pass a nail with a wrapped wire through a magnet, and you could induce a current. So it could go both ways. Magnets can induce a current, electrical movement. So there's a magnet, and again, I don't want us to visualize like all these electrons as particles. Just say a general sense of electron, electron rich, electron dense area. Well, that magnetic field will induce a current in those electrons. In turn, those electrons will create a magnet that goes against the external magnetic field. Bottom line is, the more electrons surrounding or near a hydrogen, the more shielded. Oh, so there's that term again, shielded. Shielded from what? Shielded from the magnet. So the one that I like to memorize is, well, 0 is the most shielded signal that we will typically see. That's tetramethylsilane, and that's because silicon has a lot of electrons, at least compared to carbon. So there's lots of electrons, lots of shielding, not only to the silicon, but the proton NMR sees protons. It monitors protons, and it's affecting the protons on these methyl groups. Now, if you start putting electronegative atoms on the on carbon, those hydrogens nearby will be de-shielded, because the electronegative atom is removing electron density from that proton. Okay. I wanted to jot down one more thing about these directions. So, the other way that people say that signals being de-shielded is they say downfield. The proton moved downfield versus the proton stays or moves upfield. Okay. And those terms come from the fact that, I gotta find it for us. The greater shielding leads to resonance at lower frequencies. Okay. So the greater the shielding leads to resonance at lower frequencies. So going to the right is lower frequencies of the radiation absorbed, and these are higher frequencies. Okay, let me show you an example. Fluorine is the most electronegative atom, but when we're working with organic molecules, we're more likely to see oxygen, which is the second most electronegative atom. Now, we need a baseline, okay? And I have this study sheet, and you can make the same study sheet by picking up representative spectrum, or spectra, and just seeing how different groups affect hydrogens. So for instance, let me get a base, and I'll write this down for us. So the base, or the signal where you would expect a methyl group, a CH2 group is called a methylene, a CH group is called a methine. They're around 1, okay? So what can we say? With no other influence from electronegative atoms, we have a methyl group, we have a CH2 group, okay, and we have a CH, okay, so the rest of these lines go to something other than hydrogen. this is the lowest. It's going to be 0.9 ppm. But the other two aren't far behind, 1.2 and 1.6. Okay, so what about if we add oxygen? So we have an oxygen, okay, and we connect it to the CH3. What is it going to do to that CH3? Well, we have potentially an ether, and it gets pushed downfield because the oxygen is de-shielding. This de-shielding effect. You see what I'm getting at? And we can pick up this number somewhere. Let's see if we can. I better. Let me show you how to end it. So let's see. That's a methoxy group. So Methoxy Nmr Shift. How about that? And then let's go to images and let's see how that oxygen affects that methyl group. And this is hard to read, but how about that guy right there? Do you see how over here it has O and then have a methyl and it got pushed to 373? So that's predicted. What is observed? Observed is the bold, 3.89. Let's jot that down, 3.89. This goes up to 3. And we'll round up 3.9 ppm. Okay, that's pretty significant. 0.9 to 3.9. Well, what about for the CH2? You know, the CH2 starts off a little bit higher at 1.2. So I would say, so what would be on the other side? Like a carbon here. So I would say those hydrogens would be higher than 3.9. And I'm going to estimate around 4.5. Okay, 4.5. Okay, and let's not worry about methine. Okay, but we're really concerned about the methyl in CH2 because that's going to help us interpret the NMR. Okay. Now, the way I want to go over some more de-shielding effects is we're going to look at these sets of molecules and do a little prediction. Okay. And then we'll verify looking at their actual NMR spectrum. Okay. Alrighty. Bromine is an electronegative atom. Bromine is an electronegative atom. So it's not as electronegative as oxygen. So I don't imagine. Oh, we actually don't have an oxygen methine. Because that is a hydrogen right there, a methine hydrogen. Man, we're just gonna look up this spectrum in just a bit. But you know, normal of 0.9, this CH2 would be 1.2. We gotta find the spectrum. I have all 9. Yes, I have all 9 printed out somewhere. 1, 2, 3, 4, 5, 6, 7. Okay, let's try to predict this. Let's go fall back to our other features, splitting and integral. This is a really good exercise. So this one is a 3H singlet, doublet, or triplet, or quartet. You put your finger on the house and say how many people are in the neighboring house. 1. So this is a doublet. Okay. Again, we would expect it to be 0.9, but it's not directly connected to bromine, but it's 1 carbon away, so I would think it's a little bit de-shielded. Let me see if there's actually a 3H doublet already in our... Let me know if you see a 3H doublet. Do you see how fast it could be, the process of elimination? If we know that we have a 3H doublet, maybe we could eliminate 8 of these spectra and get the one that matches. You notice I'm focusing on the area. Ooh. See that? I was focusing on 1, but because of that bromine, I bet. See, that's a 3H doublet right there, and right now that's the only one I see. Here are the other spectrum 7, 8, and 9. Look at that. It's this dude right here. That is 1.7. Okay, that's very interesting because 1.7. Okay, it's not super deshielded. Okay, but it is deshielded. Now we could focus on this one that would be pretty deshielded. This is a 1H, and we have the spectrum. Oh, what's the splitting actually? That will help us locate it. Put your finger on the house, okay, or their pen, and look at the house on the left, house on the right. 2 neighbors plus 3 neighbors, that's 5. That's a sextet. And there it is right there. 1, 2, 3, 4, 5, 6. 4.1. Okay, 4.1. See, I don't have an apples to apples comparison because I wish I had the oxygen methine over here, but I don't. I'm not going to spend time looking for it. But still, that's pretty far. 4.1? Man, 4.1 just because there's a bromine there. Because if without the bromine, a normal methine group would be 1.6. Are you getting the hang of this? There's this methyl group. That's a normal methyl group frequency. Okay, so when I say frequency, that's interchangeable with chemical shift or ppm. It's just vernacular for where it is located. So that is a I was about to say lower frequency, and yeah, lower frequency. Okay, around 1. So there really is not much influence of this bromine on that methyl group. Okay. Oh, what about that? Okay, I'm done with bromobutane. Let me just mark it so I don't look at it again. What about this ethanol? A normal CH2 group is a 1.2. So what do you think that's going to be? It's next to an oxygen. Alright, so when we draw it out, right, that CH2 group is next to an oxygen, so maybe we'll see something around 4.5. Okay. Now, this is, we may have to narrow it down from a bunch of spectra. So, let me take a look at this one. We're looking definitely for a 3H triplet. Okay, and then let's see if there's, the CH2 that's next to the oxygen. Okay, so it can't be this because it doesn't match the number of hydrogens. We have 6 hydrogens. Okay. 1, 2, 3, 4. It's not that. It could be this. Did I say 6 hydrogens? Yeah, 6 hydrogens. So it's not that. Could be that. Maybe. Whoops. It could be that. Maybe. And it could be that as well. Okay, 6 hydrogens. So I'm using the number the integral, the number of protons to figure this out. Interesting. Just from experience between those two, do you see how that CH2 group is way over at 3.7, whereas this CH2 group is only at 2.4? I bet that's the one next to the oxygen. Okay, so it went to 3.7. This has a ppm of 3.7. Okay, now we've gone into an OH group. Let me give you a couple of notes about OHs and NHs because they're kind of unique. OH and NH, or NH2, it's just a hydrogen or oxygen or nitrogen. They don't have a typical chemical shift because it's very concentration dependent. They don't have a typical chemical shift. They could show up anywhere along the x-axis. Alright. What else? That's point number 1. Point number 2. it's kind of interesting, but their signal is typically not split, and they don't split their neighbors. Okay, so you don't count these typically as neighbors, even if they are a neighbor. Like here, that is a neighboring the neighboring house, and the hydrogen lives in that house. But we're not using that to split this. This is only going to be split by the neighbors on this carbon. So we would predict this would be a quartet. Q. Oh, I keep going off screen. Q. Okay, because those hydrogens are not split by this hydrogen. So let me write that down. I'm talking about these two, are not typically split. They could be under rare circumstances, but normally they're not. And they don't split other signals. So they are not neighbors, and you don't look at their neighbors when you're figuring out what splitting they are. They are always singlets, in other words. Okay, so they are not typically split, and they do not split other signals. Okay, the next thing, bullet point number 3, and I'll put it underneath here because not only is that peak a singlet, but it's typically broad. Now, the example that I showed, it wasn't that broad. Let me see where to go. Yeah, it's not that broad actually. It's this one right here. Normally it's a little bit broader, like for instance that is broad meaning wide. So it's actually over there. They had to zoom in because there's a little hump here, and they had to zoom in, and what did they do? They zoomed in on the y-axis. They made the y-axis, they expanded the y-axis so you can see the hump. I don't have another OH example here, unfortunately, but they're typically broad. I would have expected this to be much broader. Oh wait, that's not the OH. Uh-oh, where'd the OH go? Give me 1 second. Let me find it. Oh, it's this one. Yeah, this one. I had it. Because, well, remember, I'm looking for the integral of 1 for the OH. So that's really narrow. That's more narrow than I would have expected it. Okay. Actually, as long as I have this up, let me show you a hydroxyl signal. Let's do isopropanol. Let's hope this shows the typical NMR. There we go. Do you see how this one here, it's pretty broad right here. Let me find a better example because I want to show you. Oh, here we go. We have examples of thin, narrow signals, peaks, and here's your broad OH. See, that's what I mean by broad. Okay. I'm running out of time, so let me give you a couple more chemical shifts. Aldehydes. Aldehyde hydrogens are pretty distinct. They are going to be around 9, maybe 9.5. Do I have a carboxylic acid? I have a carboxylic acid here. This is pretty distinct. I know it's an OH, right? It's the OH of the carboxyl group, but that's pretty steady. That's around 11.5. You won't find anything else actually higher than that. Now, the one that I really want to get to is this benzene ring. The benzene ring are hydrogens connected to carbon, and we saw some downfield shifting, to 3 to 4, but this is actually 8.5 to 7.5. And if it's not a benzene ring, these hydrogens here are going to be 6.5 to 4.5. I'm not going to get into why. It's a very interesting story actually for the benzene ring. Because of circulation, it's forming like a circular current, and that produces a very strong magnetic field against the external magnetic field. The thing is, the magnetic field that it's inducing goes through the center of the ring, and when it loops around, you could imagine you have your ring like this. When the magnetic field loops around, let's say the induced magnetic field goes this way, but when it loops around, it's actually going the opposite way once it hits that hydrogen. Okay, and this is a very de-shielding effect. Very de-shielding. It shields it very, very well from the magnet. Okay, so let me show you these two examples. By the way, the aldehyde, there it is, 9.5, or integral of 1. The vinyl, when you have a hydrogen off of a double bond, that's called vinyl. And the vinyl is right here, okay? 2 and 1 for a total of 3. So here you have 3 hydrogens that are coming off a double bond. And the benzene is right here, super messy. Okay, the splitting is kind of crazy due to these, due to the currents, due to the shifting of the double bonds. It doesn't quite follow the n+1 rule, but there's a 5 there. That actually represents all 5 of these hydrogens, even though you know that technically these two are the same, these two are the same, and this one's different, right, from the other two. Now with more expensive instruments, you would see the differences between these two protons, and this one. So when you're labeling the equivalent hydrogens, you're fine to say A, B, C, A, B. Just realize that in practice, A, B, and C on the ring are kind of right on top of each other. Okay. Now, I wanted to tell you the story about esters. I'll introduce it here, and this is going to be kind of important, especially if you think you have an ester as your proposed structure, because I can guarantee you. Here's the story of ester. I'll do it briefly. If I have this ester right here, okay, 1 carbon on the O, 2 carbons on the carbonyl, versus this ester right here, 2 carbons on the O, 1 carbon off the carbonyl, they actually have the same integrals and splitting, and it's only the chemical shift that's going to save us. Because look at this. We have a 3HA singlet. Okay? Eventually you'll be as fast. You're probably faster already than I am. B. 2HB, 3 neighbors quartet. Okay? And then we have C. 3 HCs triplet. Okay? Forget about the structure now. Pretend you don't know that. Pretend you only know, you see a spectrum and you see this. Well, take a look at this. I'm going to label it a little bit differently. I'm going to label this A. That is a 3HA singlet. Do you see what I'm getting at? B. That is a 2HB quartet, because it has 3 neighbors. And C. This is a 3HC. Oh no. The integrals and the splittings are the same. I know they don't represent the same protons, but you wouldn't know that. All you would see are these signals. What's going to save you is the chemical shift, because the most de-shielded group here is this A. It's the singlet that's the most de-shielded because it's next to the oxygen. In this case, the most de-shielded is not the methyl group, it's actually the CH2 group. So if you think you have one of these two, let's say you have a spectrum, and you think it's one of these two, look at the most D-shielded. Is it a singlet or is it a quartet? That's going to tell you which one it matches. And that's the only thing that's going to tell you. That is the story of esters. It's very tricky because you switch to two groups, you still have the same splittings and the same integrals. So I have that. If you want, you can pause the video. These are the effects of a methyl or a CH2 group being next to a oxygen or the carbonyl. So for instance, there's that methyl group next to an oxygen. Looking at my cheat sheet, I would say that is 3.6. So if you have a 3.6, but more importantly, if the most D-shielded signal is a singlet, it's this dude right here. But what's the most D-shielded in this case? It's the CH2 group. If the CH2 group is next to the oxygen, that would 4.3. Okay, so maybe you don't memorize the ppms. It doesn't really matter if you recognize that, oh, that 2H is the most D-shielded. Out of these two, it's this one because this is the most D-shielded proton, not this on this molecule. On this molecule, it's actually the methyl group. So not only is the most D-shielded signal a different splitting, it's actually a different integral. And okay, so this is again my cheat sheet. I have the vinyl stuff and I have the aryl or the benzene stuff. Okay. But before I leave, let me show you the two esters. It's really, I think it's a really cool story. Oh, here they are. And I'm not going to tell you which is which. You figure it out. You could pause the video. Those are the two spectrum. And one of them is this. I better give you the right structure. So both of them, see, look, 2, 2, 2, 3, 3. So one of them is that, and the other one is, okay, let me just double check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 3, 6, 7, 8, 9, 10, 11, 12. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. These are different because off of the O we have an ethyl group. Over the O here we have a propyl group. Which is which? Very interesting. Okay, because they're both D-shielded, they're both CH2s. Can you use the splitting to match the spectrum to the correct ester? Okay. With more practice, you'll pick up more ppms, more tricks. But I tried to get through the most useful ones here. All right. Good luck. And I guarantee you, there's a lot of good practice problems in your textbook.